In the last class, we were discussing about the selection procedures, the different types of selection procedures that is available in genetic algorithm or that is being employed in genetic algorithm. Selection procedures are one of the most important process that is happening in genetic algorithm, because when we have to do crossover, we have to do the parent selection process. And when in the case of mutation also, in most of the cases, mutation also, we will have to do some sort of selection process, because in most of the cases, not all the crossovers undergoes mutation. So which mutation, which chromosome undergoes mutation, for that one also we have to do some sort of a selection process. And when we are changing the generation, that is the chromosomes for the next generation are selected. In that process also there is selection. So selection is one of the most important and the most frequently used process in genetic algorithm. Now the next process in genetic algorithm is the crossover. So let's see what is a crossover and what are the different types of crossovers that is available in genetic algorithm. The most prominent crossover methods that is being used for different types of problems are described here. The crossover is the procedure by which new chromosomes or new individuals are generated using two or more parent chromosomes. So in most of the cases, only two chromosomes are used, but in some special cases, in some special crossover operators, there are they use most of more than two chromosomes or more than two individuals. So it is actually it is also known as a reproduction process. Reproduction in the sense two chromosomes interchange information with each other and they produce new offsprings, possibly or with the hope that we will get better fit offsprings. So let's see what is how crossovers are done. So the crossover is a critical feature in genetic algorithm that we have already discussed. It greatly accelerates search early in the evolution of a population. So it actually accelerates the search, the global search. Actually, the crossover is done in order to do the global search procedure. So it is mostly used for the global search procedure, and it greatly accelerates the search early in the evolution of a population. That is the better fit individuals, but the not the most fit individuals, but or the individuals which are having a fitness which is closer to the optimum is not being selected or being generated during this phase. It is the belief that during these stages, that is in the early stages of the search, only not the best fit individuals are explored, but better fit individuals are explored in that in the early stages of the search. So it leads to effective combination of schemata, that is subsolutions on different chromosomes. The schemata is actually the subsequences in different chromosomes. So schemata is actually a subsequence of the chromosome. Like in this case, this particular sequence 101, it is a schemata, or 000, it is another schemata. Or in this chromosome, if you consider this 010, it is a schemata. So a schemata is as a subsolutions on different chromosomes. So this schemata may be repeating in different chromosomes, so that then if the fitness of those chromosomes which have this particular schemata present is higher, that is all those chromosomes are having a higher fitness, then we see when we say that this particular schemata, this particular schemata produces better fit individuals. So that is the concept. So in crossover, what happens is the schemata are recombined. That is, it is the effective combination of schemata on different chromosomes are done. That is, this particular schemata is mixed with, suppose this particular schemata, that is 0, 0, 0 is good, as well as 0, 1, 1 is good. If these two schemata are working well in different chromosomes, so then if we combine, our hope is that if we combine these two schemata together, we will get a better fit individual. So that sort of thing is what crossover does. So in this case, in this particular scenario, there are two individuals, P1 as well as P2, that is two parents there. So the first parent is 0, 1, 1, 0, 1, 0, 0, 0. Then the second parent is 1, 1, 0, 1, 1, 0, 1, 0. So we define, or we consider two schemata here. This one is a schemata as well as this is a schemata. And what we do is this particular schemata is interchanged with this particular schemata of the second individual. So that is the crossover. So see, in the next, after the crossover, here the crossover happens. So this the crossover happens here. And then after the crossover, what happens is the 0, 1 of the first parent remains the same. Then 0, 1, 1, that is 0, 1, 1 from this particular chromosome. That particular schemata replaces the 1, 0, 1 schemata here. So 0, 1, 1 comes here. Then the 0, 0, 0 that stays there. So again, in the second parent, for the second parent, it is 1, 1. Then it is here also in the child also it is 1, 1, and then 0, 1, 1 is replaced with this 1, 0, 1. So it is 1, 0, 1. Then 0, 1, 0. So this is the child 1 and this is the child 2. We expect that the child will be having a better fit, will be having better fitness. But it is not necessary that in all the cases, all the childs will be having better fitness. But in most of the cases, or in many cases, we will get better fit individuals by doing this this crossover process in genetic algorithm. And for doing the crossover, we are not, whenever we are selecting two parents, we are selecting the parents with respect to some specific probability values, that is using the roulette wheel selection or using the stochastic universal sampling or any sort of those type of selection. Everywhere there is some probabilities involved. Some probability in the sense a specific individual is selected, a specific chromosome is selected based on some probability associated to that particular chromosome. So when two parents are selected, suppose these two parents are selected, but again we are checking whether they should mate or not. That is, the crossover is to be done in this particular combination of parents or not. That also we have to check. So for that one, we give a specific probability for the genetic algorithm, that is the crossover probability. And the crossover probabilities are normally taken as large values. The large values of the order of 0.9 or so. That is, out of 100 times the parents are selected, almost 90 times the crossover is done, and out of the 100 times, only 10 times the crossover will not be done. So that is the crossover probability. That is, the crossover is usually applied in a genetic algorithm with a high probability. So doing the crossover, there are actually two probabilistic operations are done. The first is the selection of the parents. It is a probabilistic operation. Then the second one is the crossover itself. It also has a probability value associated with it. That particular probability is known as the crossover probability. And the different types of crossover operators are one-point crossover operator, then multi-point crossover, uniform crossover, whole arithmetic recombination, Davis order crossover, or it is also known as order 1 crossover. That is OX1. It is shortly denoted as OX1, Davis order crossover or order 1 crossover. Then partially mapped crossover, order-based crossover, shuffle crossover, ring crossover, etc. There are so many other crossovers also, which are not much popular. Depending on each work, a writer publishes, not a writer, a researcher actually publishes. He might be introducing a new crossover operator, because combining two different chromosomes is very easy. It can be done in many different ways. So each different way will be given a different name, and so there will be different types of crossover operators. A number of crossover operators are available in the literature. If you go through literature, you will find a very large varieties of crossover operators, out of which the most popular ones are enumerated here, and we will be discussing only these types of crossover operators. So the one-point crossover, in the case of one-point crossover, what we does is a random crossover point is selected and the tails of its two parents are swapped to get new offsprings. So like this is the first parent, this is P1 and this is P2. P1 and P2 are divided into two different parts. At some certain points, it may not be at the middle itself, it can be at this position also, no problem. At a certain points, it is again based on some probability, it is also being selected. The position of the crossover point is also selected based on some probability. So in this case, in this particular case that we are considering, it is being selected at this position, in this red line, where this red line is, where this red line is shown. So here is the crossover point. So what it does is, the crossover operator actually divides these two chromosomes into two each. That is, this particular, the chromosome shown in green, it is divided into two at this junction, that is at between 4 and 5. And this one is also the second parent, the parent P2. It is also divided into two parts, that is it is divided at this junction, that is between 2 and 3. Then these two parts are interchanged with each other, that is 0, 1, 2, 3, 4, then 3, 5, 7, 5, 8. Then the second one becomes, that is this 3, 5, 7, 5, 8 is going upwards, or it is joined with the first part of the first parent. The second part of the second parent is joined with the first part of the first parent, and the second part of the first parent is joined with the second part of the first part of the second parent. So this way, this part is joined to here and this part is joined to here. So likewise, you will get two new offsprings or two new solutions. But the problem with this type of operations, this type of crossover in types of problems involving this permutation type solutions, the permutation type solutions is that there may be the possibility of repetition of the values. Suppose see here, this 3 is repeated here also, the 3 and 5 is also repeated. So these things you might have to taken care of. That is, after each crossover, you will have to change, or you will have to refine the particular chromosomes in such type of crossovers. That is, when the same thing is repeated. In the case of traveling salesman problem, as we have discussed, the same city cannot be repeated again. So if this is a permutation type, this may not be a permutation type representation problem, but if it is a permutation type representation problem, then the same value cannot repeat again. So in that case, if it is being repeated, in that case, one of that particular element is to be replaced with another element which is not present here. See, here the 6 is not present. 6 and 9 are not present here. So, but 3 and 5 are repeating again. So we have to replace this 1, 3 and 1, 5 with a 6 and with a 9. So that sort of thing you will have to incorporate in your program while incorporating 1-point crossover for problems involving this permutation type of problems. And the next type of crossover is multi-point crossover. In the case of multi-point crossover, it is actually a generalization of the 1-point crossover. So in this case, there will be more than one crossover points will be there. That is, there will be more than 2 segments. At least 3 segments will be there. See here. Here there are 2 different crossover points are there. One here. This is the first crossover point, and here is the second crossover point. So each divides the particular chromosome into 2. So here it is divided into 2, and here also it is divided into 2. So there will be 3 different 1, 2, and 3 segments from each chromosomes. So what we does is the middle segment is replaced. The middle segment is replaced with the middle segment from the other one. So like this 4, 2, 3 goes in this place, in the place of 3, 4, 5. So here is the resultant chromosomes, that is the offspring chromosomes. 0, 1, 2, then instead of 3, 4, 5, it comes 4, 2, 3. That is 4, 2, 3. The blue thing is the blue cells comes here. Then again the green cells repeats. So here the first 3 is blue cells, then 3 the green cells, then finally again the blue cells repeats. So this is the multi-point crossover. In the case of multi-point crossover, it is not limited to only 2 crossover points. You can use more than 2 crossover points also. 3 or 4 crossover points can also be used if your chromosomes are long enough. In this case, in the example displayed here, if we use 3 crossover points, then each segment will be very short. So that is why we are not, that is not represented here. But 2-point crossover, this particular case is known as 2-point crossover. If you are using 3 crossover points, then it is known as a 3-point crossover. So it is so likewise, you can increase the number of crossover points, and the name also changes. A generalized term is multi-point crossover. Then the next type of crossover is uniform crossover. In the case of uniform crossover, we are not dividing the chromosome into segments, but what we does is we treat each gene separately. So we know that each position represents a gene. So what we does is we treat each gene separately. So for the first position or the first gene in the offspring, what we does is we select one of these 2. Here there are 2 genes, 0 and 5. Out of these 2, we select only one for the first one, and obviously the second one, the remaining one will be included or inserted into the second offspring. So in the first offspring, we are selecting randomly one of the genes, and the second one, into the second chromosome, we are inserting the other one. So in the 0 or 5, so 5 goes here and 0 goes here. In the second position, that is then the second gene, it is 1 and 8. So 1 goes here and 8 goes here. Then next 2 and 9. So 9 goes here and 2 goes here. Then 3 and 4. 4 goes here and 3 goes here. So likewise, randomly one gene is assigned to one chromosome, and the remaining gene is assigned to the second chromosome. That is the uniform crossover. This is selected with a uniform probability. That is, there is a uniform probability of one particular gene being selected for the first offspring chromosome. Say this is, if this is O1 and this is O2, there is a uniform probability of 0 and 5 being selected to the first offspring, that is O1. Then once this one is selected, the remaining one will go to the second chromosome or the second offspring. So that is how this uniform crossover is done. Again, in this case also, if you are going for a uniform crossover in the case of permutation problems, again you will have to do some refinement operations after the offsprings are generated, because there is again a chance of the same value being repeated. See here, 4 is being repeated twice and 5 is being repeated 4 times. So 1, 2 and 3, etc. 2, 3, 6, etc. are missing. Again, 9 is also being repeated. If this is the chromosomes being represented for a traveling salesman problem, then obviously this particular chromosome will not be a feasible one. Okay, this one is also not a feasible one, because the 5 is repeating thrice, 3 times the 5 is there. So the next one is whole arithmetic recombination. In the case of whole arithmetic recombination, it is being used only for numeric representations, because in the case of permutation type problems, this cannot be used, or this is not much being used. So in this case, what we do is for the child one, we take alpha x plus 1 minus alpha of y, and child 2 alpha of y plus 1 minus alpha of x. So this is x and this is y. So we take some values, some constants alpha and alpha. Alpha, say it is the alpha can be 0.1, 0.2, etc. or 0.9, depending on our problem or our instance of the problem. We can define the value of y, define the value of alpha. In most of the cases, alpha is taken as 0.5. So what it gives is, this is if alpha is 0.5, this will give you 0.5 times x plus 1 minus alpha, that is again 0.5 times y. So this is the simplest way of you doing this all arithmetic recombination. So this is x and this is y. So 0.1 and 0.2. So the average of these two. If alpha is taken as 0.5, in the case if alpha is taken as 0.5, the value of this will be the average, 0.1 divided by 0.1 plus 0.2 divided by 2, that is 0.15. So that is the value. So if it is in this case, in this particular case that is shown here, the alpha is taken as 0.2, I mean 0.5. So that is why this 0.1 and 0.3, it is 0.2 each. But the problem with this type of crossover is that both the offsprings will be the same. See, both the offsprings 0.15, 0.15, 0.2, 0.2, again 0.2, 0.2, 0.2, 0.2, 0.3, 0.3, 0.25, 0.25. So all the genes are the same in both the chromosomes. That is, both the chromosomes are the same. So that is the problem with alpha equal to 0.5. If we take alpha equal to 0.5, both the chromosomes will be same. So you have to select some other value. In most of the cases, you will have to select some other value for alpha in order to get two different chromosomes out of a crossover operator. I mean crossover operation. So that is this is possible. This type of crossover is done in the case of problems involving numeric representation. Then the next one is Davis order crossover, or it is also known as order 1 crossover. How this is being done? This is being done in a special way. That is, it is a permutation based crossover. That is, in the case of permutation based representations, chromosome representations, this particular crossover is very useful. This particular type of crossover is very useful because after the crossover, none of the elements will be repeating. None of the elements will be repeating after the Davis order crossover or the order 1 crossover. So suppose we have two different crossovers, two different permutations, two permutation chromosomes here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9, 7, 0, 2, 8, 1, 4, 3, 5, 6 is the second chromosome. In this case, if you see, none of the elements are repeating. So here, none of the elements are repeating. Here also, none of the elements are repeating. So this is a permutation representation of chromosome. So in this permutation representation, what we do is we first select a specific schemata from both the specific positions from the from both the parents, like this 3, 4, 5 and 6. So this particular position is fixed for the first one. So 3, 4, 5, 6 is fixed here. Then what we do is we start inserting the remaining elements. The remaining elements are inserted in the order it appears. In the order it appears in the second chromosome. So that is 3, 4, 5, 6 is fixed here. Then what we do is we start from the first position in the second chromosome. So 9, 7, 0. That values are inserted in the chromosome in that order itself, from the point where we ended inserting the points from the first chromosome. So 3, 4, 5, 6, it is the common, it is fixed. So 3, 4, 5, 6 is fixed, and from this point onwards we start inserting those values which are not present in the first in these elements, and the order in which they are inserted is the order in which they appear in the second chromosome. That is why it is known as the order 1 crossover. So 970, so 970 is inserted. Then 2814, 281 is inserted. 4 is already there. 4 is already there. 3 is already there. Then 5 is already there. 6 is also already there. So this is the way in which the chromosome is generated. So in the case of the second chromosome, this is only one chromosome, only O1 is generated. If you have to generate O2, so in that case what we do is we take the fixed points as the points from the second chromosome. So if we take it, it will be like this: 2, 8, 1, 4. So this 2, 8, 1 and 4 are selected. Then we insert the remaining elements from the first chromosome. So in this case, 0 is not in here, so 0 is inserted here. 1 is already present. It is the next item is 1. 0 is inserted, then the next item is 1. 1 is already there, so we can omit it. The next item is 2. 2 is also there, so we can omit that one also. The next is 3. Then 3 is inserted here. Then 4 is already there, so we don't have to insert 4 again. The next is 5, then 5. So this we reached the end of that particular chromosome. Then we have to start from the beginning. So 5 is inserted. Now the next is 6, 7, 8 and 9. So somewhere I made a mistake, I think. 2, 8, 1, 4, 0, 3, 5. Happened. 2, 8, 1, 4. That is there. 0 is inserted. 1 is not required. 2 is not required. 3 is required. 5 is required. Oh, okay. 8, 6, 7, and 6 is inserted. 7 is inserted. Then 8 is already here. So 8 you don't have to insert. Then again 9. So this will be O2. So this is how the chromosomes, the order 1 crossover is done, or the Davis order crossover is done. So first we pick the elements, pick 2 crossover points, and the elements between these 2 points is kept fixed, and then the remaining elements are inserted into the offspring from the second parent in the order they appear within that particular chromosome. So that is how the order 1 crossover is being employed. So these are the main crossover operators that is being used in most of the problems in genetic algorithms. The other crossover methods are not much used, but they are also available in literature. So with that one, we end the topic, crossover. And with that one, I hope we can end today's session also. We can continue with mutation in the next session.